talk about mineral commodities and energy. There is a very tight link between both of them. First, because the whole and the entire infrastructure surrounding us is made of raw materials, and this includes also the infrastructure of energy production and energy consumption, which means that without raw materials, we are not able to use energy, and we are not able to produce energy. The other connection is that in order to produce these raw materials, we consume a lot of energy. So we will consume energy to produce the raw materials which are used to produce energy. In a changing world, in the title, so there are at least three main changes we can identify. First, an increase of population, a variation, an evolution in the landscape, economic landscape, with the very fast growth of populated countries like China since 30 years, India, part of the Asia-Pacific region could also follow the same path, and maybe Africa tomorrow. So all these evolutions, both these evolutions, entails an increase in the consumption of both energy and raw materials. And the last change, which is quite important, is a technological change. The energy transition belongs to that. We have to build a brand new infrastructure which consumes, again, raw materials with a change in the variety of raw materials we will use, and also in their quantities. This is something I will talk about in this talk. The penetration of information and communication technologies is another example of this technological evolution. And in both cases, we need new raw materials, as I said, and in some instances, the same mineral commodities. So over the last decades, there is the question whether the availability of raw materials could put a limit on our ability to build this new infrastructure that we need. There's a very abundant literature about that. I won't even try to give an overview of that. It would be too long and probably boring. Moreover, the outcomes or the results of these studies are strongly dependent on the hypotheses we make for the future. So instead of that, I would like to rather discuss basic questions, for instance, which are listed here. What are the main drivers of consumption? What do historical trends tell us? Can we define a baseline evolution using historical data? And finally, if we are able to answer these questions, what can we reasonably anticipate for the future? So this will address the question of models. Which kind of models we used? We don't use the same models if we are geologists like me, or economists, or people working in the social sciences, or engineers, and also the question of scenarios. So very briefly, before entering into the details, regarding the raw materials and mineral commodities, we can define two groups. The first group corresponds to this, what I call structural commodities, which are produced in very large amount, more than 1 million tons every year, up to several billion tons every year, like cement or steel, for instance. So cement, steel, and its alloy, also aluminum, copper, tin, lead, and all these metals which are used since many hundreds of years, and which are used to build the base infrastructure. Bon comme ça, non? It's not important. Which are used to build the base infrastructure of communication, housing, food production, heavy machines, and so on. So these base metals and these structural commodities are mainly used by countries which are in course of the economic growth and development, like China, for instance, which still consumes about half the steel produced globally. What you see on the figures on the right is the evolution of steel consumption in red, and what you see is that after the Second World War and the 70s, there is a strong increase at about between 3 and 5% every year. This is the period when presently developed countries built their infrastructure. Between the 70s and 2000, the increase is much lower. And then at the end of the 90s, we have still a growth period due to the development of China. Then there is a second type of raw materials, what I call the technological commodities, used in technologies that did not exist 40 years ago. Mainly in the sector of energy, for instance, rare earth elements in the permanent magnets of wind turbines, gallium, indium, selenium in the multi-layered technologies of photovoltaic solar panels, lithium, cobalt, graphite in lithium-ion batteries. Also in the sectors of information and communication, so a mobile phone contains about 50 different metals, and we all have a mobile phone in our pocket. In the 80s, 10 metals were used to build a computer. Nowadays, it's almost all the periodic table. And a variety of use. For instance, I just took this example in the light-duty vehicles, where we have now screens or displays. We have lots of electric motors to open the windows, to move the seats, which contains rare earth elements. So all these applications are responsible for a very strong increase of use. About 10% every year, which means that we double the consumption every 5 or 6 years. And this is these elements which have focused most of the attentions over the last decades, and which are, the question is whether the availability of these raw materials could put a limit to our ability to shift toward low carbon technologies. So again, I will not discuss that in details. My point is that if we want to project ourselves in the future, well, we will have to work, of course, on the demand, both for resources and energy, but also on the production capacities. And this includes the primary production, but also the recycling of metals. We will have to work on the possible substitution, which has been mentioned this morning. And this has been done in a very highly dynamic system, with technological changes, with socio-economic changes, with new environmental constraints. So we need definitely dynamic models to do that. And my view of the problem is that we also have to use models which are able to reproduce the past trends if we are, before attempting to use them for the future. It's, I think, a very important point. The most simple model we can think of is drawn here. We have a technological infrastructure, so it's a stock of cars, of a building, or whatever, which produces services. These services, it's housing, producing food, clothing, transport, and communication, and so on and so forth. In order to make this structure operating, we need, of course, energy, and in order to build the infrastructure, we need resources. Then the metabolism here of the society and using this infrastructure produces waste in form of heat and chemicals. So it's very simple, but actually it's a bit more complicated than that because there are many connections here. First, the demand, the level of services, it depends on the economic development of the country, and I will show that it depends on the GDP per capita, which will control the level of energy and resources demand. Then we can also see that the end-of-life products, which are considered as waste here, can be recycled and they become a resource which can be used and re-enter into the technological infrastructure. There is a connection between energy and resources because we need energy to produce the resources. We need resources to build the infrastructure producing energy, and this infrastructure is contained in this stock. So even with a simple model, we realize that the problem is not that simple. If we now look at the global scale, all countries developed at their speed, and they are not isolated from the rest of the world. There is a lot of flows of energy and raw materials between all these countries. So again, even with a very simple model, we come with a complex problem which has economic, physical, environmental, social dimensions. So we have to find invariants that we can use to work on the long time scale. An example of this invariant, if we look at the evolution of raw material consumption, we have here copper, aluminum, and steel, as a function of GDP per capita. So you have in the y-axis here the amount used per capita per year. We see a common evolution at low GDP per capita until about $20,000 per capita. There is a strong growth, which corresponds to this period of building the infrastructure. And then after, let's say, $25,000 per capita, there is a decoupling of the consumption versus the increase of GDP per capita. You can see that for the metals here. You can also see that for the oil consumption, although the level of saturation, so when the line here becomes horizontal, can be higher, for instance, in North America than in Europe. But the basic observation is that we always have this sigmoid evolution. It's a logistic function.
It's a developing of the growth, but not
we still use, yeah, sure, but there is no growth anymore. Yeah. And the reason for that is that the infrastructure also is also a logistic function of the GDP per capita. If you look, for instance, at the number of cars per inhabitant as a function of GDP per capita for different world regions, you also see this saturation when you reach about 0.8 cars per inhabitant, which is normal, actually. When everybody has a car, it's not necessary to have one more because you can only drive one car at a time. And if you do the same for the number of locomotives, or ships, or aircraft, or built area, you observe the same trend. So if we are able to represent this evolution with the same equation for all world regions, it means that it gives us a baseline evolution for the future. If we combine now this evolution of the number of cars per capita as a function of GDP per capita, and we have an evolution of the GDP per capita as a function of time, we are able to estimate the car fleet so how much car there is in a country as a function of time. And this is very important because, again, it gives us some constraint about the future evolution. I'm showing here an example, the baseline evolution for France. So on this figure, the blue symbols here are observed data, and the red line is modeling we make with a model we develop in our team. So the agreement is not perfect, which is normal because we use the same logistic function for all world region, but it's not that bad. So once you have the infrastructure, you can calculate how much energy you need for this infrastructure. You can calculate how much raw materials you need to build the infrastructure. Here, this is the copper amount, which is used to in the sector of housing. In blue, in red, it's energy production. In green, in the sector of transport, and so on and so forth. You can also calculate, once you have the energy for a given energy mix, how much CO2 or greenhouse gases you produce. And finally, the local contribution of the country, here France, to the global warming, which is about 0.03 degrees by the end of the century. So we are on France is 1% of the global population. So it means that we are on a trend corresponding to 3 degrees global warming. What we see here is that the final energy consumption decreases with time, which is normal because you don't change that much the infrastructure, but you improve the technologies and the energy efficiency. So it's normal that we observe a decrease here. So if we do the same calculations for developed countries, we observed always the same trend. This is the copper consumption in North America, Europe, and developed Asia. So we are almost at the steady level. The situation is completely different in China, with a very strong increase. We are nowadays here, which will continue for the next 10 or 20 years before reaching the saturation level here. India, possibly, and developed Asia. And of course, it's the sum of all these contributions that give us the evolution at the global scale. So although in developed countries, the consumption is predicted to be quite stable, it will strongly increase at the world level. Of course, this is a baseline evolution that I showed previously, and we want to get away from this baseline evolution because, for instance, the CO2 emissions here decrease not fast enough compared to this arrow, which shows the SNBC, Stratégie Nationale Bas Carbone evolution. So in order to go faster, a simple way to do that is to change the technology and increasing massively the electricity as a source of energy and, of course, a low carbon energy. This will create new needs in resources and energy to change this infrastructure. Why? Well, the first reason, I think, is because renewable energy is abundant, but it's a very diluted energy. So if you want to capture the renewable energy and transform it into a usable energy, you need big infrastructures. An example of which is shown here, it's an offshore wind turbine, 6 megawatt capacity. So this guy is about 200 meters high. It contains 1,500 tons of steel, permanent magnet with something like 700 kilograms of rare earth elements. But if we look at steel only, so 1,500 tons for 6 megawatt corresponds to 250 ton per megawatt capacity, which is higher than the same steel intensity of power plant burning either fossil fuels or nuclear combustible. If we now shift into produce energy, we come to the conclusion that the material intensity of renewables, so now in ton per megawatt hour, is 5 to 10 times that of conventional power plants. Of course, this is changing with time, and technologies are improving, and so on and so forth, but still, it gives an idea of what costs in terms of raw materials, the shift from fossil fuel to renewable energies. Just an illustration here, I use two scenarios which have been published by the International Energy Agency 7 years ago. So I like that because we already have some possibility to compare what was expected at that time with the present situation. The first one is quite conservative, but still in agreement with, or in line with the Paris Agreement. We have 30% renewables here in 2060. The second one is much more ambitious, with 70% renewable. So now I show the cumulative demand for the first scenario and for the second scenario. And as you see, in the second case, the cumulative demand for copper, iron, and aluminum is 2 times higher. Of course, the energy chain is not restricted to the production of energy. Let's have a look at the road transport, for instance. So in the first case, the amount of battery electric vehicles is quite low. In the second case, it's a massive increase in the battery electric vehicles. The demand for cobalt, if we assume that batteries will be NMC batteries, so with a cobalt electrode. In the first case, the increase of cobalt demand is quite low. In the second case, it's huge, and it is even higher than the cobalt reserves estimated by the United States Geological Survey 4 years ago. Of course, these reserves will change with time, but still, it gives an idea of the challenge.
What was the green one?
So the green one is the scenario you have on the right-hand side. Yeah, you have plug-in and hybrid. Hybrid, it's in red, and plug-in vehicles in red. Now, regarding the share of the primary versus recycling, as I said previously, the end-of-life product can be recycled and reincorporated in the technological infrastructure. But if you are in a period of growth, it's not enough. You have not enough to recycle, so you have to use, in any case, virgin material coming from the mine. The other point, which is important, is that 100% recycling is impossible, so, which means that at each recycling loop, there is a loss of raw materials. In the case of copper, if you have a recycling rate of 60%, meaning that 1 kilogram of copper, which has been produced 30 years ago, is recycled at 60%, it means that every 30 years, you lose 40% of the matter, which has been balanced, which has to be balanced by a new incorporation of virgin material. So what we see here is that if we only look at what is incorporated in the infrastructure, we necessarily underestimate the needs because we don't count this loss of raw materials. The second thing we understand from this very simple sketch is that the recycling flow here will depend on the amount of end-of-life product, which means that these end-of-life products were produced many decades ago. And again, in a period of growth, there is such a change in the size of the technological infrastructure that the available end-of-life is very low compared to the present consumption. I can illustrate that by comparing the case of China and Europe. China, this is the case of steel with a lifetime of 50 years. The amount of steel which is available in China was the amount that has been produced 50 years ago minus the loss associated with the recycling, minus 20%. So, of course, again, 50 years ago, the infrastructure was much lower in size than the actual demand. So the recycling can be only quite low compared to the demand, which is shown by the black curve. This is why China needs so much primary steel. The situation is completely different in Europe, where the infrastructure 50 years ago was approximately the same as today, so our potential of recycling is much higher, and this is why we use much less primary steel. Now, the situation is a bit more complicated because we tend to export our end-of-life products towards developing countries in form of scrap. This is recycled elsewhere. And then, of course, the finished products which are produced here come to us, which means that we export our pollution and we import energy in form of finished product. So few words, I will be quite short, but few words about the production capacities now. So we are able to estimate the demand, but how can we estimate the production capacities? So if you remember, that was the evolution of the copper consumption I already shown before. This is a flow, so it's in million tons per year. Now, if we integrate this flow to estimate the stock which has to be produced, from the antiquity until now, so over the last, say, 3,000 years, we have produced 800 million tons of copper. For the next 30 years, we will have to produce the same amount. If we want to go until the end of the century, we have to produce 2 billion tons of copper, 2 additional billion tons of copper. Again, this is a huge challenge that can be illustrated with this slide, what it means. I'm showing here a photograph of a historical copper mine in Utah. This is a big hole. It's 3 kilometers long, 1 kilometer wide, and 1 kilometer deep. Do you have any? So the small dots you don't see here are these huge tracks used in open mines. Do you have any idea how much copper we have produced from this hole in 100 years of time? I give you the world production actually of copper is about, let's say, between 20 and 25 million tons. What do you think? We have produced more or less than 20 million tons from this hole? Less? Much less? We have produced approximately the same amount. We have produced 18 million tons from the copper from this hole, and 6 billion tons of rocks have been extracted. Okay? So if we want to follow the trend I showed on the previous slide, we will have to produce 44 of such mines in 30 years, 130 for the next 80 years, and the story doesn't end by the end of the century. So it continues, because we have to not only to grow the infrastructure, but to renew it, to maintain it, and this costs, of course, raw materials. There are lots of environmental impacts. I just show here in terms of water demand. We need 200 cubic meter to produce 1 ton of copper. Which means that for the next 30 years, the amount of water is about 200 cubic kilometer, corresponding to 2 times the Geneva Lake. If you divide by the number of people, it means that to produce this copper, we use about 1 liter per day per capita. I'm only talking about copper here, 25 million tons every year. Aluminium, 100 million ton, steel, 1.5 billion ton, and so on and so forth. So clearly, the environmental impact are real, and they are always focused where you produce. So they are very localized. If you have an environmental impact, you have, to some point, a social opposition. And it's not only in the developed countries, it's also in developing countries. One example here, the Salvador in Latin America makes history as a first nation to impose blanket ban on metal mining. And it's written in the law. This followed huge pollution of surface water and a competition of use of water between agriculture and mining. Okay, another limit might be the exhaustion of reserves, the peak oil and the peak metals. I'm showing here the results of our Australian colleagues regarding the production of copper. It should decline to 0 by the end of the century, and everybody is dead. The demand is the orange curve, so you see that there is clearly a misfit here. So is it serious? I don't know exactly. I'm showing here 100 years ago, Mr. Joralemon, which was really not stupid, from Harvard, and he was CEO of a copper mine. This guy said us that the age of electricity and copper will be short at the intense rate of production that must come. The copper supply in the world will last hardly a score of years. Our civilization based on electrical power will dwindle and die. This is not exactly what happened, clearly. In contrary, if we look at the reserves, the copper reserves over the last 100 years, we see that these reserves steadily increased, although at the same time we have produced more and more copper. So how is it possible? It's possible because at the same time the average ore grade of copper deposits decreased. 100 years ago, we are able to extract copper from rocks containing 3% of this metal. Nowadays, so these ore deposits are exhausted. Nowadays, the average ore grade is 1%. And there is much more rocks containing 1% copper than rocks containing 3% copper. So if we are able to follow this trend, we mechanically increase the copper reserves. But of course, the problem is that you need, at constant technology, you need much more energy to extract copper from diluted rocks than from concentrated rocks. On this slide, I'm showing the energy you need to extract 1 kilogram of metal, different metal, as a function of their dilution in natural rocks. So here you have platinum, gold, very diluted metals, and here iron, manganese, aluminum, which are very concentrated. And basically what you see is that there is in a log-log space, you have a straight line, meaning that the energy is a power law of dilution. If you do the same with the price, you observe exactly the same, meaning that the price primarily depends on the energy you need to extract the metal. This explains why lead is cheaper than gold. So if we continue on this trend, decreasing the ore grade, of course, we expect to have an increase of both the energy consumed to produce the metal and the price of this metal. Of course, the red dots here are a snapshot. It's the representation at 1 year, in year 2005, in this case. But in course of time, we are able to improve technology. And this is why the price of metals has not been increasing very fast over the last century, simply because we were able to improve the technology. The price of energy is, of course, important also here to transform the energy into price. If in the future we are able to decrease the price of energy, which seems to be a dream, but let's accept this idea, by a strong shift to renewables, for instance, we might be able to decrease the price of metals, even in this context of ore grade reduction. So I will skip that and that. By using all this approach and these evolutions of the ore grade of metals, but also on the quality of oil and gas and coal we extract, I show here the results of the modeling. This is the price of different metals as a function of time. In blue, you have the observation, so the real price, deflated price, and in red, it's what we calculate. So again, the agreement is not perfect, and we are not able to represent all the short-term variations, which are really due to economy, but the long-term evolution seems to be correct, and we anticipate a possible sharp increase of price in a close future if we continue to increase the price of energy, so if we stay with hydrocarbons. So finally, the future availability will depend on the price we are willing to pay, environmental and social impacts we are ready to accept, and the price of energy, of course. I will skip that, I will skip that, and I will skip that to come to the conclusion, which are very tentative. So the question of mineral and energy resources availability is clearly not new, but it's expected to become increasingly binding in the future, so that minimizing the use and maximizing the recycling are, of course, crucial. The future demand will depend on technological and economic scenarios, for sure, but not only. It will depend also on geological, geopolitical, environmental, and social dimensions, which are very difficult to address. There is no single path for the future, but for sure the future constraint will be different from the past, and because there are always a thermodynamic limit that you cannot go below, which means that forever improvement of technologies is not possible. I did not discuss that, but believe me. The absence of shortage is not a sign of abundance, it's a sign of technological progress that masks the degradation of resources. It's true for raw materials production, it's also true for fishing, for instance. We are able now to fish the last fish in the ocean without shortage. And once this last fish will be fished, then suddenly we face a problem. For mineral resources, the question is finally, can we envisage new unconventional resources for metals? I think it's important to not confuse economic and physical constraints. So the physics will always have the last word. And Freddy asked me to say a few words about the possible place of mathematics on this topic. So I think there is no simple and definitive solution to complicated and highly dynamic problems. So mathematics are clearly essential to formalize these problems and to provide the tools and approaches that will help to find solutions. Thank you very much.